Okay, all set. So next up we have Matt Kear talking about his rather marvelous, Matt Kear, my apologies, we're talking about his rather marvelous thrust stand system that he's developed. And so Matt, are you ready to go?
Yeah.
Okay, very good. Over to you, Matt.
Brilliant. Let me just get screen sharing working. Okay. So hopefully you can all see the presentation and hear me okay?
Yep, all good.
Brilliant, thank you. Okay, so hi everyone. Well, good morning, good evening, wherever you are in the world. So I'm Matt Kear, and I'm just going to talk a little bit about the ArduPilot based thrust stand that I've been developing. This was essentially a sort of one of those really satisfying, fun projects that I started, and it ended up becoming a very useful tool. And it's a very useful tool I'm hoping to share with the community to make something that's just a little bit more accessible for a bit more in-depth vehicle setup. Okay. So a little bit about what I'm going to talk about. So a lot of the design decisions I made throughout this are very linked to sort of the aims of the project. So I'm going to cover those quickly first. Then I'm going to share a little bit around the actual sort of development history, because I think it's fun to look at where things came from and how everything was like super hacky to begin with, and that's all the really fun bits. Then I've sort of split the thing down into two. So there's the actual main controller unit, which can literally be plugged into any load cell based thrust stand. And then there's an actual measurement unit as well, so that adds additional features above and beyond what the sort of normal stuff that you can just buy off the shelf will give. Then there's a little bit around like, okay, well, what data do we actually get out from this, and then how we're going to use that. So I've started making a little post processor as well, which again just makes it a little bit easier for people to just plug this data in and get some useful information out. And then finally, I'll just talk about the future work planned. Okay. So the project aims then, so the idea was basically I wanted to add a new tool into the ArduPilot ecosystem. So, we use a lot of electronic motors, speed controllers, and props, but I don't think that the community has easy access to the ability to really compare and contrast different setups, basically. And there are things already available, but they aren't very feature rich. They're very basic. It's often you're reading thrust data off of a little LCD screen, or you're having to shell out a lot of money. So it was to try and make something that was very feature rich, but also very accessible. So what I mean by accessible is I try to keep it low cost. And so everything I'm presenting, if you were to make a carbon copy of what I'm presenting here, it'll cost you something to the tune of about £340 for everything. And I've tried to be as limited as possible in sort of the manufacturing, because this is some hardware. So it's using predominantly 3D printing and then just basic hand tools. And then so this builds on some of the work from Peter Hall, that he wrote the Lua scripting access to the I2C bus. And so this actually provides, in my opinion, quite a nice way of incorporating a driver for an external device into scripting. So it's a really nice way to see that, and then gives people a flavor for how you can kind of prototype those drivers in Lua. And then the other thing I wanted was basically just to offer as much flexibility as possible. Like, you don't have to do exactly as I've done. You can take bits of it and just make it your own. And that's part of what makes it a really fun project. So like kind of some of the history, just to kind of show what I started out with. So the very sort of beginning was very simple, in the sense that so what I took was one of these off-the-shelf units that I bought off Banggood for about £40–50, something like that, and then a SparkFun load cell amplifier, and then plugged that into my Cube Black and just like started prototyping away to get something basic working. Then I started trying to add more sort of hardware in around that, and you'll see later that a big part of this was trying to make everything very flexible to easily change over speed controllers and motors, that kind of thing. So a lot more hardware and sort of like a dedicated flight controller that's going to go inside the box all started appearing. And then the really fun bit, which is like getting to play with LEDs. So and screens and things like that. And so you can just see some little demos of the first prototypes of the throttle bars that I made with the addressable LEDs, and then using the OLED screens that we've got available in Notify to start displaying some of that data. So this is kind of where it all began, and just getting some of the basics working. So I have already mentioned that it does, this is all done in Lua scripting, and there are very minor changes to ArduCopter or ArduPilot. So all the examples I've got, the vehicle I have loaded on the flight controller is ArduCopter, but it doesn't matter too much. And there's a couple of outstanding PRs that I need to tidy up to try and get in, and then this script will just work on currently master, but probably 4.1 when that's released as beta. So the controller unit itself, and I should say I've got there's a Discord thread as well. So a lot of the information I'm sharing now will be that I've spoken a bit about on that Discord thread. And if you've got any other questions in the future, I want to follow along on that thread. So talk about the controller unit itself. So some of the features. So there's a Dead Man's Pendant, which is just a momentary push button on the top. And you've got to have your thumb pressed on that, even when the system is armed, for any of the motors to run. So it's just a nice safety feature. And it's on like a flexi phone cord so that you can stand far away from the device. So like some of the props and motors I've tested make terrifying noise, and so it's pretty good to be able to stand away from all of that. Then we've got an arming switch with the obligatory sort of missile cover. Some aux switches. So I originally just added these aux switches as because potential expansion for the future. There was with nothing specific in mind. There's still nothing tied to aux 2 at the moment, but aux 1 is now for switching throttle modes. So there's transient throttle modes and ramp throttle mode, and I'll talk more about those later. Then there's the calibration button, and so that just takes you through the process of calibrating the load cells, and in this case it's both thrust and torque load cells. And it's a nice little button with RGB LEDs in there, so that it changes color as you step through the different phases of the calibration. And the OLED screen talks you how to go through each thing, apply your load here and press the button again, that kind of thing. So this one is set up so it'll do between 4 to 14S voltage, like a lot of things that I mess around with, sort of around the 12S voltage range. So that was a big feature for me. And then we've got the throttle bar with the addressable LEDs, and that will display the max throttle. So using the user scripter params, you can set what the maximum throttle you want to actually run to is. So if you want to do like reduced tests in certain regions of throttle, you can. And then when you're actually armed and running, you get the change in color bar to represent current throttle. Now this is a really nice way to be able to sort of see, where you are in your progress of test, but being able to stand really far away, so you can't actually see what's being sort of output on the OLED screen. But that screen does output what throttle mode we're currently on, the thrust, torque, current, and voltage values, and that's like particularly useful when you're sort of just trying to make sure everything is working and you're close to the setup. So you can push on the load cells and make sure you're at least reading some sensible values, that kind of thing. But the screen unfortunately is a bit too small to be useful up close. But we can tie in with ground stations for all that information, so we can stand far back from everything and still see all that information anyway. I should say as well, if anybody has any questions as I go, please do just interrupt. I'm happy to just take questions as we go. So This is the back of the control unit now. And this is basically the main interface to the speed controllers. So we've got a little screw terminal for being able to access the ESC telemetry. So from everything from like BL Heli 32, that kind of thing. Then we've got DC power output. Now you'll notice that I've used these terminal blocks. And so again, one of the big parts of this was like, I wanted to be able to switch things over very easily without having to constantly solder and desolder things. And I wanted to test different configurations of speed controllers with motors. And so part of that was just making it very easy to switch things over to these terminal blocks. So then we've got throttle output, and that's we're running ArduPilot, so we get all the protocols that ArduPilot has as well, which is brilliant. Not that that specifically matters for doing thrust stand testing, but one of the nice kind of fallouts is that this gives you an opportunity to play with a setup and sort of kind of start to get a feeling for how to set that up. So if you've never set up one of those protocols before, again, it's just a really nice thing that you can do on the bench with this. Then we've got some little hold down pegs, so we can just mount the ESC in place and keep it fixed. As I previously mentioned, when you start using 12S plus, that's 50 volts. You don't really want cables being able to move around and risk shorts or risk touching the wrong part or anything like that. So this helps just keep everything held down in place and safe. And then finally, so this is the terminal connections between the three-phase from the speed controller, and then the motor wires will plug in the other side. Now, underneath this terminal block, then I've attached one of these little hobby wing electric commutation sensors on 2 of the phases. And so what's quite nice is even if you're using speed controllers that you don't have ESC telemetry, just by the nature of like plugging your speed controller in, you're automatically getting some way of computing your RPM from your electrical commutations. Without any additional hassle of trying to solder or plug things in. So I apologize for the slightly messy wiring inside. I probably should have spent a bit more time trying to tidy that up, but to give you an understanding of what's going on inside this box. So we've got ESP Wi-Fi telemetry. So this is brilliant because I can so I tend to sit with Mission Planner open and I use a telemetry screen so I can see live outputs. Whilst being far away from the test setup. I can use it for using MAV FTP to pull all the data back across, or just setting the params, that kind of thing. So this makes it really nice to interface with everything. Then there's a buzzer hidden down in there, so you get some feedback using standard ArduPilot notify. Then you've got there's a Mauchbeck for the high voltage down to 5.3 volts, nice clean stable voltage from that, and the high current Hall effect sensor sat there as well. Now the flight controller I've got in here is the Maytech F765 wing. So the reason I chose that was basically it's the low-cost controller that has these features. So these features are what was kind of critical to be able to set this, or the things that I needed basically. So the script is quite beefy now, and so it does really need a F7H7 processor on it. To be able to use 2 of the strain gauge amplifiers, they both have the same address. So I've used 2 I2C buses to be able to overcome that problem. There are other ways around that because you can definitely sort of use a MUX to have them both on one bus, but this is just my approach. And then you need an analog in for your voltage and current coming from the current sensor. Now, I know that there is inbuilt current measurement and voltage measurement on this board, but it's nowhere near the voltage that I was personally interested in. Hence why I'm not using that here. Then you need 1 UART for being able to use the telemetry, and 9 configurable GPIO pins. So so that's for our output, for our addressable LEDs, for our sort of read in on the RPM from the hobby wing, that kind of stuff. Now, whilst physically attached to the actual measurement unit, I include these as the as part of the control unit, and that's these sort of SparkFun quick scale amplifiers. Now, these are the bits where the driver for talking to these over I2C has been added into Lua, and basically these are the sort of the only components that it really makes sense to use these over anything else if you want to use that Lua script that that I've written, purely because the driver's already there for them. And then just another feature, which is like a software overcurrent protection. So I've got this little demonstration. So using a user scripter param, you can set the maximum current you want to, you do not want to exceed. And then whenever you do exceed that current, it trips and cuts all output to the motor and stops the user from still trying to run anything. And, you know, nice LEDs making it very clear that you've tripped that overcurrent. So that's quite a nice way for doing some protection of your hardware as well. Obviously, I set the current incredibly low with no prop on that motor for you to see. Okay. Any questions on the control unit before I move on? Super. So the measurement unit then, now this was created partly because one of the things I was personally really interested in is being able to measure torque. And from what I found online was typically you're either looking to shell out a lot of money for a thrust cell, like for a thrust stand setup, you know, or you're going to have to kind of make your own, and hence I started making my own. Now, the design I landed on was to mechanically decouple torque from thrust. Now, I'll talk more about that as we go through, but there are a number of different options, and I've seen people be very successful with sort of not having that mechanical decoupling and just using software to sort of post-process the torque and thrust out from two different load cells. So the actual components in this setup then, so we've got the motor mount, which is just 3D printed. And the whole idea here is we need something that just to easily be able to change motors over. So you can just change this basic adapter for whatever motor you need. Then we've got the actual shaft. Now to make this shaft, it's basically an 8mm 3D printer shaft. And then I printed some grinding guides with PETG, and then like just using a grinder, like a grinding disc, just took it down to those guides. So, you know, this certainly doesn't need to be precise at all. It's all done by hand, but you know, you get a neat enough output, and it's certainly good enough to very efficiently transmit the loads through this main shaft. Sorry, going the wrong way. Okay, so some of the components like I've got on here aren't modeled in that 3D model we've got in the background. So just overlaying a picture. And so we can see, so the graphite lubricated linear bearings, there's 3 of them in this in total. And so the reason they're in there is because with this mechanical decoupling, I still need to allow some form of motion. And so we're allowing the shaft to move linearly back and forth through that bearing, and we're allowing the shaft to rotate. So any resistance in rotation is applied purely through the torque load cell. And I tried a couple of different approaches, and I found that these linear bearings are they're actually bushings. These graphite bushings were definitely the best way of doing this, and certainly the simplest. And one of the really nice things that kind of falls out of doing this mechanical decoupling is that any like once per rev vibration that's coming from our setup is being resisted mechanically resisted by the actual thrust stand itself. And so that's not being fed back into our sensors. And that was a big driver for wanting to go down this route, because I had tried just simply attaching 2 load cells, and I found that there was just a lot more noise on the output. So this has ended up giving a much cleaner result. The disadvantage of this approach is that it does represent like having a lot more hysteresis in the system. But I've done some things in post-processing to just check that and overcome any issues that it may raise. So I'll talk a bit about that later. So then we've got some thrust bearings and then the actual collar which holds the thrust bearing in place. And then this back piece is what I call the thrust cell interface. And that basically is, so we're trying to apply thrust only, but no rotations. And I'll explain more about how that's achieved shortly. Then we've got the thrust load cell itself, the torque load cell, so a point load bearing mount. So one of the things I wanted to make sure is that we're not actually twisting this load cell on its axis at all. So there's a bearing which sits down in here. So there is a point load that's always in the center of that, that load cell. The actual attachment of that load cell into the main shaft, and then a lug which allows us to put a little arm into the top so that we can apply a known moment to the shaft for calibration. So looking at a cross-section of the thrust cell interface gives you a bit of a better idea of what's going on. So there's a thrust bearing here and a thrust bearing here which aren't modeled then, but we've got the sort of holders just behind them. And then sat down inside here is another one of those graphite bushings. So what this is doing is the thrust bearings are resisting any lateral motion so that the thrust can be applied to the thrust cell. But those bearings and the graphite bushing allow the shaft to still rotate. So no rotation is applied, and therefore no rotation is resisted by that that thrust cell, by that thrust load cell. All of the rotational resistance is coming from the torque cell. I hope that makes sense. Oh, I labeled this and stepping ahead of myself. So this is something that a few people have asked me about on the Discord sort of thread that I've been talking to people on. And so hopefully this will help cover off a few questions. And there's been a fair bit of interest around how the torque measurement is being done. So we're looking at a cross section of where the actual torque load cell is. So the components here, you can see the actual shaft, and so this has got one of the grinded flat spots on it to really help the load cell attachment to grip to it, and there's bolts that run through there as well. So this is our load cell, and then this is the mount that holds this bearing. So and then here's the housing that bearing presses against. So basically, the reaction torque from the motor is applied to the shaft. Now, the only thing in this system that then resists that is the reaction load down on this bearing. Now, this means that it gives us the ability to actually measure the torque through that load cell. And finally, just a little sort of breakdown of the actual motor mount. So there's again a flat spot, and this is an interference fit, so there's a lot of friction in here as well. Then there's 2 bolts that run through here through lugs, and then there's actually the bolts to be able to mount into the back of the motor as well. Now my background is in sort of aerospace mechanical engineering, and so I just get really interested by this stuff. So I made some pretty pictures from a simulation that I did of a couple of the different parts, because when doing this stuff with 3D printing, there's always this big question as to, is it going to fly off at me, or there's a safety aspect to it. So I set up this simulation of like an anisotropic material, so that these are printed 100% 3D printed infill. The main reason for that is to make it a little bit easier for me to simulate and get a bit more confidence in that we're not going to be, it's not going to be failing. And so you can kind of see how the load is being applied and where the main stress is appearing on those bolt lugs. This is conservative because I've not actually accounted for the interference fit and the friction on that surface. So anyway, everyone likes pretty pictures. So the actual data output. So the data is being dumped to a CSV file, which can be easily accessed using mavftp. The main reason, well, there's two reasons for the CSV file. One, it was just the easiest way of doing it actually in scripting, and two, it's also the most accessible form of data. So you know, nobody's tied to actually using the post process that I'm using. You can quite literally just put this in Google Sheets or in Excel and plot the data yourself, and so the barrier to entry there is very low, which is I found appealing. So I've got a list of the data fields that are currently being stored and output, which I've largely talked about already. Just a couple of the points is that the actual RC out, so I'm using ArduCopter as the vehicle, so I'm actually using the mot PWM min and mot PWM max parameters to set the max and min PWM out or throttle bands basically. And then similarly, because we're using the ESC telemetry, if you're using an ESC with telemetry, then you just need to make sure that the servo BL heli poles is set or configured correctly for your motor to actually get a sensible reading for the ESC RPM. And something which I've never even really looked at before, but it's really useful for the thrust stand is actually the ESC temperature. It's not the most high fidelity output, but honestly, this was great because I've been close to melting some ESCs, and so it's really nice to have that temperature output. So another function that we could add potentially is a temperature protection, much like the current protection works as well. So you know, this is showing some of the actual data that we're getting out, and it's quite nice to contrast between the two throttle modes. So I previously mentioned a bit about this. So we've got our nice sort of gentle throttle ramp. Now, what this does is just gently increases the throttle and then holds 10 increments all the way up to max, and then steps all the way back down. So you can loosely see in the thrust, there are actually two traces. There's the run up and run down. Now we're doing that to be able to attempt to capture any hysteresis in the system. And I hope you'll agree that there is very little in this system. So when I started seeing some of this data coming out, I was very pleased. This is for mainly, you know, what's our max thrust and how we, you know, what's our, you know, we can use this data then for our thrust expo parameter for linearizing our output ready for ArduPilot. So then a little bit more niche, but very interesting, I thought was so this transient mode. So the way that the transient mode currently works is it reuses the hover throttle parameter. So you set whatever value your vehicle is going to hover at based on using your ramp. So once you've set that value, it'll slowly ramp the throttle to hover, and then it will start applying a like step inputs based on a table that's in Lua either side of that hover throttle. And so where I was interested in this is for looking at speed of response of some different motor propeller configurations. But one of the really nice things is I heard Leonard talk a lot in the past about, you know, the difference between the speed of response of torque versus thrust. And you can categorically see it now, like torque, as soon as the change is applied, we get this humongous spike and we don't actually manage to capture the peak of torque. And so the torque is instantly applied and then it comes down to some steady state constant. Whereas thrust, you don't get that same spike. That's thrust slowly, comparatively speaking, ramps to that. You get that roll off in thrust. So that's really nice to be able to sort of physically see something that that I've heard a lot about in the past. So there's still some work needs to be done around throttle mode transients, because at the moment it's not very user friendly in terms of being able to configure, because to have a sensible point of comparison between two different setups, what we're actually caring about is that we need to have this step change needs to be a consistent thrust change output, so that we can measure the thrust output versus time. And at the moment, because we control via throttle, I have to say I want a 20% step change. I have to come in here and actually measure or look on our throttle ramp what that 20% throttle is, and then go and input that into the table in Lua. So I need to do a little bit of work just to try and make that a little bit more front end accessible through some parameters, perhaps, to make that easier to set up. Okay, and then the post-processor. So I've started putting together a post-processor, and big asterisk, this is really clunky at the moment, so I need to do some work to tidy this up. But it's Python-based and using Tkinter for the GUI. Then it's very useful for, you can just output and plot the raw data. It has automatic run detection in it. So if you've done multiple ramp ups and ramp downs in one log, you can actually separate those out so that you can look at those individual runs separately. It's not shown here, but there is support for taking data from other thrust stands. So there are other automatic thrust stands that they output in CSV formats. So you can take that CSV format and you can convert them to what this process is looking to see. Then we've got a number of filters. So sometimes the data can be very messy. So this is just a way of trying to clean that data up. Then we've got some automatic expo fitting. Again, this needs a little bit of refinement, a little bit of work, but it works in the exact same way that the Google Sheets works. And again, having that CSV file, you can just drag and drop the data from the CSV file into the Google Sheets that we have on the wiki, and it just works. And then I've also got coax grouping as well. So this is a crude, but it does work way of looking at coax data from this thrust stand. So you can see we've got the actual sort of measurement unit here, and then we've got this sort of dummy holder for the other second motor. And what we do is we run the motors in one rotation so that we've got thrust going in one direction. So it's hard to tell from the image, but let's say, for argument's sake, this is currently the bottom motor. So the thrust generated will be going in this direction. So this will be the top motor, that'll be the bottom motor. And then we flip the motor rotations and the propellers, and then we can then measure this as the top motor and this is the bottom. And for these motors that were on test here, here's some of the data that came out. So you can see you've got the top motor and then you've got the bottom. And what the coax grouping allows you to do is basically add the two together. So you can see there's been some interpolation and some filtering just to bring that data. It's quite minor, but it gives you the total output, which then allows you to use to apply your thrust linearization to a coax grouping. Is this method perfect? No, but it's pretty good. And one of the cool things that kind of I noticed coming out of this, and I haven't actually got a graph to show this, but in this coax setup, the top motor, the thrust profile is essentially the same as if the motor was on its own. It's largely unaffected by the bottom motor. Now that's probably something to do with, or probably more related to this specific setup more than anything, because the disk loading on these props is very high. The exit velocity from these propellers is very high. But basically all of the inefficiencies and all of the losses in this coax setup are all coming from the bottom motor. And with this kind of setup, the high sort of throttle region we're getting significant losses. So I'd need to look at more data, more motor setups, but this is starting to indicate that there may be a genuine, how can I say, case to start doing per motor throttle expo, so that we can do per motor handling in coax setups, so that we can try and achieve something with that's a little bit more efficient, but we're still having the redundancy that some of these coax setups tend to afford us. So future work then, I'm currently working through a bug in the Lua script whereby every now and then the thrust data sort of just stops working. Now it's something to do with the I2C bus and the it's not like a setup with the amplifier or anything like that. It's definitely a firmware issue. So I'm just trying to kind of work through that at the moment before this kind of gets pushed in. So then I want to tidy up the post processor because it's a bit of a mess at the moment, and then that code can be released and everybody can just modify it as they please or add things or that sort of stuff. Then eventually I want to go to a larger measurement unit. The thrust capacity on this, I've taken this measurement unit up to 10 kilos, but it's a bit small for that, and it all gets a bit terrifying as well. So I'm going to make a bigger one, but without being quite as constrained on the price. So it is larger. And then what I want to add into that larger one is the ability to do dynamic mass balancing of props and motors for that larger unit as well. And that brings me to the end of the talk. So thank you for listening and welcome any questions.
Fantastic. Thanks, Matt. Just a quick note about that Google sheet. I wouldn't completely trust that sheet. That was done by me originally. It was based upon a MATLAB script from Leonard. And then I sort of translated MATLAB. And given I'm not actually a MATLAB programmer in the first place, that was one source of dodginess. Plus, there was a little bit of confusion regarding the spin min and the definitions of where things happen at the low end. And so Leonard and I went backwards and forwards several times, and I don't think we got to a final resolution on having the definitive Google sheet that's definitely the one you should use. Yeah. So I'm not offering you a solution here. I'm just pointing out that I wouldn't take it as gospel.
No, that's entirely fair. And when I say that it works, the extra fitting that I've done works in the same way, I mean in that it still handles the voltage scaling. It's still. But it's essentially automatic, and so you kind of hit a button and it just configures all of the values to what it try to optimizes the curve. It does a best fit basically.
I think we need some reference data sets, and those reference data sets need to be probably gone over manually by Leonard to get what the reference expo out of that data set should be, and then ensure that our tools like the sheet and your tool produce something close to that manually calculated, because Leonard does a whole lot of little tweaks and things when he looks at a set of data. I'm sorry for talking out of turn, Leonard. I know it's your baby, but I think a reference data set with the correct answer would be a great way of us ensuring that we consistently produce something that the end users will get some value out of.
Okay. Yeah, it's a little bit tricky too in that like the voltage scaling is one of the most important things, but part of it's there's some approximations in the code. The knowing what your spin min, spin max is actually going to be, not just your minimum maximum PWM, changes that expo because it narrows the range, especially the spin min. The higher that is, the lower the expo, because you're working. So there's a few things like that where you can't actually calculate the true expo unless you know what your spin min is that the pilot or that the aircraft's going to use for that safety thing at the bottom. But the equations themselves are pretty straightforward. It's a bit that I struggled with trying to do it in this. I'm used to running in MATLAB, so.
Yeah. And look, Google Sheets is a terrible way to program. It's just very accessible. right?
Yeah.
That's why. You mean lots of people can easily just, hey, I'll just copy this sheet, throw in my data, and I'm done. They don't need to buy a copy of MATLAB, and it runs on every platform. But as a programming environment, God, it's awful. It's silly.
Yeah, it's
terrible.
I'm sure we could do better. And I've went through, must have been 20 iterations of it to try and get it.
I mean, maybe a JavaScript, would be better. Actually, a JavaScript web page might actually be better, because at least it's a somewhat sane programming language. But anyway.
But yeah, great job, love it. I've
thanks.
done the same, something similar. My motors and propellers are a little bit bigger than what you're using, and perhaps a little bit scarier. I do envy the 5-inch props, but yeah, I sort of did mine was just an Arduino thing, but it yeah, I went through a lot of the similar things. I ended up doing a tri-dual strain gauge version to get torque, and it's great because what I didn't see in any of your pops is the motor efficiency calculations and that sort of stuff that's right there in that data as well, that I found really useful and interesting from my results. So yeah, great work. I was looking at that enviously. What sort of update rates are you getting on your strain gauges?
So on the throttle ramp, I'm just using 10 Hertz, but then for the transient, I'm up to 80 Hertz.
Yeah, because they say 80 Hertz, but it didn't look like I could, with my test, and it might have been my strain gauges or something, but it didn't look like I could actually get far, like I would see I could output it fast, but it was like the strain gauges took a while to change value. I wasn't getting the instantaneous response out of the strain gauges, so I didn't feel like I could get an accurate time response, because I wanted to measure the reaction time of the motors in exactly the same way you did, but you seem to have got much faster response time.
I think it depends on your amplifier more than anything, because that's certainly what's limiting this thrust stand is the rate of the amplifiers. And the thing to be clear, so I'm requesting 80 Hertz, and when I'm looking at I've got a little plot which shows how that the actual logging rates was being achieved, and about half of them are being achieved at about 80 Hertz, and you can see there's a lot of dropped data. Now, I don't know at the moment whether that drop data is just because of noise on the bus, or whether it's just because I'm just pushing that amplifier a bit too hard. So still to kind of be worked out.
Yeah, for me, it wasn't the amplifier, because I'm using exactly the same amplifier you are. For me, it just seemed to be the actual the response of the strain gauges was slow, and it might, I don't know why that would be, but yeah, I just was wondering if you'd seen anything like that yourself. Like when I look at these things, I'm probably doing something wrong with something silly somewhere, but I've
never noticed that, but I mean, I'll certainly look for it. I never considered it purely because I know that people have used strain gauges for measuring quite high frequency vibration, and so I am surprised by that, but like it's definitely something I need to look
well, that's why I was surprised too, because when I saw your data, it looked like you got really nice fast responses on your torque and that sort of thing that I didn't. So yeah, so I don't know what I'm doing there. But yeah,
sure. Brilliant, thank you.
All right, well, thank you very much, Matt. That was absolutely brilliant. Love the project, and really appreciate you coming and presenting at the Dev conference this evening. So I will just switch over the